Welcome to this week's first lecture. Remember, in the last lecture we have seen the step response types for second order systems. If you remember, we call a second order system in standard form as follows: Vn square s square plus 2 psi omega n s. Sometimes instead of omega n I said Vn or Wn, sorry for that, plus omega n squared. So this is a second order system in standard form, and remember we have defined these parameters that is called the damping ratio, that is shown by psi, and we have defined the parameter omega n. And omega n is the undamped natural frequency of the system. So remember we have seen some response types for this system, and the response types are determined by the damping ratio of the system. If the damping ratio is 0, then of course I'm talking about the step response here, response of this system to a step input. So this is my input. If damping ratio is 0, our response is purely oscillatory. So we have a response of this type, and the oscillations are not damped anymore, and which means that we have continuous oscillations lasting forever. Okay, so if I am controlling a mass, the position of a mass, that mass oscillates forever back and forth, and this is the case when psi is equal to 0, and this is the undamped case. So if I increase psi above 0, then if psi is between 0 and 1, we have the underdamped case, and in that case our oscillations are damped, which means that the oscillations converge to 0 at the end. So we have a response of this type. This is the underdamped case. So we see that again, if I'm controlling a mass, then that mass oscillates for some time around the desired point, and then it settles at the desired point. So this is called the underdamped case. And on top of these, I can actually try to draw the overdamped, the critically damped and the overdamped cases. So when I have a critically damped system, I would have a response with similar to this red curve, and if I have an overdamped system, then I'm going to have a slower response which converges to the desired point much later than the critically damped case. Okay, so we have our responses given like this. I have the red curve as the critically damped, and I have the green curve as the overdamped system. So in general, we choose the underdamped case over these response types here. If we would like to design a control system, in general, our first choice would become the underdamped case. So we somehow prefer oscillations to the overdamped or critically damped cases. So of course this is only possible in some areas of control where this is acceptable, where oscillations are acceptable. Sometimes oscillations are not acceptable at all. Of course, in those cases, I have no other choice than either the critically damped or the overdamped cases. But if the oscillations can be tolerated, people usually choose the underdamped case over the critically damped or overdamped cases. So when can oscillations be undesirable? So the examples are many. So suppose that you want to design an elevator, a control system for an elevator. An elevator is asansör in Turkish, and actually it's coming from French. So here we want the elevator to come from 0th floor, from the basement, to the first floor. Okay, this is like giving a step response to the elevator control system. The elevator is originally at the 0th floor, at the basement, and we want the elevator to come to the first floor, which is the step input here, kind of step input. And can you imagine what happens if you design the elevator control system as an underdamped control system? So what would happen if you design the elevator system as an underdamped control system? This means that elevator is going to start to move quite fast, and it's going to reach the desired floor. But then it's going to pass the desired floor, and it's going to come to, for example, the 1.5th floor or the second floor, and then it's going to go back and pass the desired floor once more, and it's going to go back towards the basement a little bit, and it's going to oscillate back and forth between the floors until it converges to the first floor. It is really an undesirable experience for a person in an elevator. Okay, so really, with the elevator control system, we really do not want an underdamped response. So what do we want in that case? In that case, I would try to make the control system as critically damped, because it's faster than the overdamped case here. So with a critically damped response, the elevator is going to start from the basement, and it's going to continually approach the first floor, and it's going to converge to the desired floor, and will stop there. So the second thing can be, suppose that I would like to design a robot arm control system, and suppose that what I would like the robot arm is to hold this cup. Okay, suppose that I'm controlling the fingers of the robot arm in order to be able to do that. Suppose that this is the 0th position, and this is the 1 position. Okay, so I want the robot arm fingers to come from the 0th position to the position of 1, whatever 1 means in that case. So what does it mean for the robot arm, or for those fingers, to have an underdamped response? So in that case, what the robot arm is going to do, the fingers are going to do something like this. They are going to come to the desired point first, but they are going to pass the desired point, and they are going to oscillate back and forth, and then they will converge to the desired point. But this is a cup that I would like to hold with the robot arm, and this is quite stiff. Okay, this is not elastic. So when the robot arm goes beyond the desired point, it is going to squeeze the cup a little bit too much, then the cup is going to be broken at the end of this motion. So in such a case, we would not really like oscillations. But some other times oscillations are acceptable. Suppose that I would like to bring the robot arm from this point to that point. Then the oscillations might be acceptable, because there is nothing to hit here, or there is nothing to squeeze on this side, and the oscillations can be acceptable in those cases. So what would be the two response types doing in that case? If I choose the overdamped case or the critically damped case, the robot arm would move slowly from the initial position to the desired position, and it would stop like that. But you see that the initial part of the underdamped response is much faster than the overdamped or critically damped cases. So if I choose the overdamped case, the robot arm is going to be quickly coming to the desired position, and then it would be stopping there after oscillating for some time. Okay, so I think the reason of the selection of the underdamped response, selection of this over this, is somehow psychological. So even if the convergence is about the same time, so a robot arm coming slowly from the initial position to the final position is somehow looking worse to the people than it coming fast towards the desired position and then oscillating around the desired position a little bit. Okay, so actually the main idea from this discussion is that we most of the times, when the oscillations are tolerable, we would try to design the control system in an underdamped way. So we would like the response to have this form when oscillations are acceptable. So I want to start new from this point. So this was a comparison of the underdamped, overdamped, and critically damped cases. Now we're going to specify that we are going to be working with an underdamped system case, okay? And we're going to try to come up with some performance measures for the underdamped response case, okay? And we're going to be trying to make a connection between the pole positions of the underdamped system and the response properties. Okay, so here let me start with the transient response characteristics. Transient response characteristics for an underdamped second order system in standard form. So this is going to be the topic of the first lecture, and in the coming lectures we are going to see the underdamped and the critically damped cases, and we are going to come up with performance measures for those cases as well. But we are going to define first our performance measures on an underdamped response. So I will first try to draw a generic underdamped response here. So this is my unit step input, and we are trying to examine the underdamped response here, y of t. So it usually looks like something like this, okay? So we start from the origin, and then we oscillate for some time, and then we converge to the desired point with some decaying oscillations, okay? So what can be some performance characteristics for such a response? This is the time axis, so that is my time. And the first performance measure that we are going to use for a system having this type of response is going to be the rise time. Then this is going to be the rise time of the system. And I will define also peak time. That is going to be the time that the response reaches this peak. And then we are going to define the maximum overshoot. So how much we exceed the desired point here, how much we exceed the desired response, what is the maximum amount by which we exceed the desired response, that is going to be called the maximum overshoot. And finally we are going to define in how long time we converge to the desired point. That is going to be the definition of the settling time. But before that, I would like to examine the pole locations of the underdamped case. We have already done this, but I need to repeat it here. So remember, in this case, we have the pole positions for a second order standard system is given like this: minus psi omega n plus minus j omega n 1 minus psi square. This is the pole locations for the second order underdamped system in standard form. So I have in that case complex pole locations. So here, remember, this part is called also omega d. That is the damped natural frequency. So the pole locations are just like minus psi omega n plus minus j omega d. And remember, in the earlier lecture, we have seen that the distance of these poles to the origin is just omega n. So let us try to remember the pole locations here. They are on the left-hand side, because this is a positive number, minus this number is a negative number. So I have minus psi omega n somewhere here, and I have j omega d here, and j omega d is nothing but j times omega n 1 minus psi square. Okay? And remember, we are actually drawing a circle here, sorry, this is wrong. So remember, in this case, the pole locations are on a circle with radius omega n, and omega n is strictly larger than omega d. Why is that? Because in the underdamped case, psi is between 0 and 1. Okay? Therefore, this number is between 0 and 1, and when I multiply it with omega n, I get a smaller number. Omega d in magnitude is smaller than omega n. So the pole locations are on a circle with radius omega n here. If you take the square of this number and take the square of this number and sum those, you would get omega n square. If you take the square root, you would get omega n. So the pole locations are here and here. And the real part are minus psi omega n. And the imaginary part are nothing but j omega d and minus j omega d. Okay? And when I look at the distance of these poles from the origin, this distance is just equal to omega n. Alright? So these are the pole locations for a second order underdamped system in standard form. So now let us try to define our performance measures. The first performance measure is going to be TR, the rise time. Okay? So its name is rise time. It is the time instant at which the response hits the desired value for the first time. Okay? Of course, in a control system, I want TR, the rise time, as small as possible. I want a fast response to towards the desired value. And the second time instant that we are going to be interested is going to be the peak time. So this is called TP, peak time. And this is the first time instant that the response makes a peak. So we see that the response makes a peak at infinitely many times here. That is why I need to say this is the first time instant that the response makes a peak. And then we are going to be defining something called maximum overshoot. So it's going to be this distance. All right? So this is called MP, the maximum overshoot. That is our maximum overshoot. Sometimes, if the actual response is not converging to the value 1, we are going to define and use something called percent overshoot. Okay, so this is going to be, so this is the absolute overshoot here. So MP is the absolute overshoot. The difference between the peak response and the desired response. Okay, so that is the absolute maximum overshoot. And sometimes, if this response is not converging to 1, then that means that in the standard system there is a scaling. So that means that I cannot use this absolute maximum overshoot in my calculations. Instead, we use something called percent overshoot. Okay? So this is shown as MP percent maximum overshoot, and its definition is something like this. So it is this is my output y of t, y at TP minus y at infinity divided by y at infinity. Okay? And sometimes since we are using the percentage sign here, we just write here times 100%. Okay? What does this mean? So in this simple case, we have y infinity equal to 1. Okay? So this response converges to 1 at the end. So we have yTP is here. So this is y at TP. yTP minus 1. So this is, the numerator here is the absolute maximum overshoot. Okay, this is the absolute value, and this is a relative value. This is a relative value relative to the infinity value of the response where we are converging. So suppose that this point is 1.1. So it doesn't look like 1.1, but let me say it is 1.3. Okay, in that case, the maximum overshoot is just the difference between these two values, 0.3. And what about the percent overshoot? MP percent becomes, this difference is 0.3 divided by y infinity is 1 here, okay? And in that case, I have 0.3 here multiplied by 100, okay? So percent overshoot becomes 30%. Okay, so the absolute maximum overshoot is 0.3 and the percent overshoot is 30%. It is the 30%, this value by which we exceed the desired response is 30% of the desired response. Okay, and this is quite a large maximum overshoot value. And we generally would accept an overshoot value, a percent overshoot value between 0 and 10 or 0 and 20 at most, okay? Percent, of course. So then why is this useful? It is just like multiplying the absolute maximum overshoot with 100 here. This is useful, the percent overshoot is useful when the final value, when the desired response, when the response of the system does not converge to the value 1. Okay? If this value is not 1, where we are converging is not 1, we always use the percent overshoot in that case. If the response is converging to somewhere other than the value 1, we always use the percent overshoot because we will know the exact formula for that percent overshoot when the response does not converge to the desired value 1. Okay? So in that case, what would happen to this formula? So suppose that this response is scaled by 0.5. Okay? All points here are scaled by 0.5. And if there is such a scaling, this MP value will be scaled as well, okay? The absolute overshoot value is going to be scaled. It is YTP minus Y infinity, okay? But we might see here that the percent overshoot will never change. However small value I scale this response with. Suppose that I scale this response with 0.5, then if you use this formula, you would still see that the percent overshoot is 30%. Okay? But you would see that the absolute overshoot value is also scaled with the scaling constant that we use. So this is my percent overshoot. It really doesn't hurt if you always use the percent overshoot, okay? Even when the response converges to the desired value 1, you can use the percent overshoot and you won't be in trouble in any way. And the final thing that we are going to define is the so-called settling time. So the settling time is shown by the letter TS. Okay, so I have this as the settling time. And in this case, there are two definitions actually, 5% definition and 2% definition. So when we talk about settling time, we generally specify which settling time we are talking about. Okay, so this is the 5% settling time and 2% settling time. Settling time is related to how long this response takes before it converges to the desired value. Okay? So if I look at the 5% settling time, obviously you see that this convergence happens as time goes to infinity. So there is no exact convergence mathematically here. Okay? But we would like to use some we would like to come up with some performance measure to actually measure the amount of time that this convergence is happening for a second order system. Okay? So obviously it is not acceptable to say that settling time is infinity all the time. Mathematically it is infinity, but we would like a more useful definition here. So here is what we do. So I define here a range, okay, around the desired value, okay. So this point is 1, this point is 1.05, and this point is 0.95. So this is called as the 5% range, okay. So this is 5% range. And of course, if I am more ambitious, then I can also define a 2% range here. So this range happens to be this one, and this point is 1.02 and 0.98. And this range, this red range, is called the 2% range. Okay? So then how do we, with these ranges, we define what the settling times are. So the settling time, 5% settling time, is the time instant at which the response enters the 5% range and it never leaves afterwards. Okay? So 5% settling time is the time instant at which the response enters the 5% range here and it never leaves afterwards. So if I look at this case, I see that this response at this time instant enters this 5% range and it never leaves afterwards. Okay, so this is my 5% settling time. Okay? And what about the 2% settling time? It is similar. It is the time instant at which the response enters the 2% range and it never leaves afterwards. Is it this time instant? The answer is going to be no. If I look at this time instant, I see that the response actually leaves the 2% range after this time instant. So this point really cannot be the 2% settling time. Instead, I need to look for the intersection between the response, which the latest intersection between the response and this 2% range boundaries. Okay, so this 2% settling time would be this value. Why is that? Because at this value, at this time instant, the response enters this range and it never leaves afterwards. Okay, so this is my T settling 2% time. Okay. So obviously, if you compare these, then you would get this type of relationship. So 2% settling time is a more ambitious settling time value, and it really requires some precision, more precision than the 5% settling time. So 2% settling time is in general larger than the 5% settling time, which we observed already here in this figure. Okay? Now, here is what we are going to do. Remember the name of this topic. The title of the topic that we are trying to cover is time domain analysis. And time domain analysis is about making a relationship or finding out the relationship between the Laplace domain quantities and the time domain quantities. So these are our time domain quantities: rise time, peak time, settling time, and the maximum overshoot. They are related to the time response. The function of time, they are related to this function of time. And what about the frequency response quantities or Laplace domain quantities? They are these pole locations. So what is the relationship between these pole locations and these performance measures? So how can I make sure that these are useful? So if I have the relationship, the exact relationship or approximate relationship between these pole locations and that response here, I can actually do my control design in the Laplace domain completely. So I really do not have to think about the complicated time functions. I can instead consider the pole locations and try to adjust the pole locations so that my response, my step response satisfies some performance requirements. What might be those performance requirements? So for example, I might want 5% settling time smaller than than some value. So in the robot arm case, probably you won't be satisfied if this convergence takes 2 days. Okay? The robot arm starts here and then it ends up at the desired position after continuous oscillations, and in 2 days it stops. You really do not want such a case, okay? So you want settling time much smaller, 1 second, for example, or 0.1 second. You want this convergence in 0.1 second. And in the elevator case, you want the elevator to come from the basement to the first floor probably in a few seconds. You really do not want to wait 20 minutes for an elevator to reach the desired floor. Okay? So here we are going to put some performance or assign some performance requirements to our control systems, and by changing the parameters of our controllers, we are going to try to achieve that performance requirements in the Laplace domain by trying to adjust only the pole locations of the system. So similarly, we can try to say that we want the maximum overshoot to be maximum overshoot to be smaller than 10%. Okay? In the robot arm case, probably we really do not want the robot arm to swing with a very large amplitude, because it can be a security issue in that case to the humans around the robot arm. So we might want only 10% maximum overshoot. So it comes to the desired point fast, but it exceeds that desired point with a very small amount, and then it would come back and it would converge to the desired value. Okay? So we want maximum overshoot to be small, we want settling time to be small, we want rise time to be small, and we're going to place some requirements onto our control systems, and without even thinking about these time functions, we are going to try to achieve those performance requirements in Laplace domain by adjusting our pole locations in the system. That is the good thing about using Laplace transforms here. So if you want to try to adjust this time function in the time domain, it is quite a complicated issue. But in the Laplace domain, this just amounts to placing the poles of the Laplace transforms at the required positions. And by just adjusting the roots of some polynomials at some desired points, we are going to achieve our control aims, or we are going to achieve our performance requirements in Laplace domain, and the design is going to be an easier thing than dealing with these complicated time functions. Okay? So here the first thing that I'm going to do is to derive the analytical expression for this response. What is this response? And then what I'm going to do is that after I find the analytical expression of this response, I'm going to find TR, TP, TS, and MP using some formulas about these parameters, Laplace domain parameters, psi and omega n. So the aim of this lecture is going to be to express rise time, peak time, settling time, and the maximum overshoot in terms of the frequency or Laplace domain quantities. So I have time domain quantities here. This is my function with respect to time, and this TR, TP, TS, and MP are time domain quantities. They are our performance requirements, or they are going to be our performance measures. And I want to know the relationship between these time domain quantities and these Laplace domain quantities, psi and omega n, or these pole, which determines the pole locations here. Okay, so I want to find a formula expressing what TR is in terms of psi and omega n. So here let us start by finding the expression of this response here. All right? So how do I find it? I'm going to find first the Laplace transform of that response. So remember, we know that the Laplace transform of the output of a system is y of s is equal to the transfer function times the Laplace transform of the input, u of s. In this case, our input is a step input. We are trying to calculate the step response. So this is 1 over s. And what is the transfer function of the system? It is going to be the second order system in standard form. Okay? So this is going to be omega n square divided by s square plus 2 psi omega n s plus omega n square. Okay? I will take them. I will multiply these two functions, Laplace functions, and then I will try to take the inverse Laplace transformation. So I have omega n square divided by s square plus 2 psi omega n s plus omega n square. So then what I'm going to do is what we always do in taking inverse Laplace transformations. I will first write this in terms of its partial fraction expansion. So this is a over s plus bs plus c. Remember that in this case psi is between 0 and 1. So the roots of this polynomial here are going to be complex. So that is why I will keep it in its polynomial form like this. Okay? I will not try to separate this into these individual first order factors. I will keep this as it is. Okay? And I have s square plus 2 psi omega n s plus omega n square. So of course I think you should know what to do from this point on. You equate the denominators and you match the numerators between the right and the left hand side. Okay? So here I will not repeat this operation. So in order to save some time here, I will cheat a little bit from my notes and I will write, if you equate the denominators and if you match the numerators to find ABC, you would find A is equal to 1, B is equal to minus 1, and C is equal to minus 2 psi omega. So please check these values by completing the partial fraction expansion and then finding the ABC yourselves. Okay? Here, in order to be able to save some time, I have written them from my notes. So then what happens? So then this y of s becomes 1 over s, and I have here minus b, minus 1, and I have minus 2 psi omega n. So I have here minus s plus 2 psi omega n divided by s square plus 2 psi omega n s plus omega n square. Okay? So now I have to take the inverse Laplace transformation of such a function. The first term is easy. This is just the constant 1. This is the unit step function in time domain. And the second one is going to be more difficult. And we know that the response is oscillatory here. The poles are complex. That means that we are going to have some sines and cosines in the response. Okay? So here, in order to be able to take the inverse Laplace transformation of this term, I need to make some effort here. Okay? The first thing that I'm going to use is this fact. So I know that sine omega t has the Laplace transformation omega s square plus omega square. Okay? And cosine omega t has the Laplace transformation s over s square plus omega square. And what happens if I substitute here, instead of s, if I substitute s plus lambda? Okay? What would be the time function corresponding to this Laplace transformation? And suppose that I do the same here, s plus lambda square plus omega square. What would be the time function here and the time function here? Remember, instead of s, if I substitute s plus lambda, then that means a multiplication by an exponential function in the time domain. Okay? So this is e to the minus lambda t sine omega t, and this is e to the minus lambda t cosine omega t. Okay? So these are the Laplace pairs that we are going to use while trying to take the inverse Laplace transformation of this function. So the first thing that I'm going to do is to bring the denominator into a form which resembles these denominators, okay? So in order to be able to do that, I will complete the denominator into a full square. Okay, so let's try to do that. 1 over s minus, the numerator is s plus 2 psi omega n, divided by, if I complete these first two terms in the denominator into a complete square, what do I get? This is going to be s plus psi omega n square. Okay? If I expand this square, I would have s square plus 2 psi omega n s, the second term, plus psi square omega n square. Since I don't want that term, I need to subtract it. Psi square omega n square, and I have this third term still here, so I have omega n square. Okay? So this is the same denominator as I have here. This is the same denominator that I have here. So here I'm going to combine these two terms here. These are going to make in omega n square parentheses 1 minus psi square. Okay? Omega n square minus psi square omega n square is in omega n square parentheses 1 minus psi square. Now I want you to look at this part. Omega n times square root 1 minus psi square is nothing but omega d. Okay? So here, therefore, this constant here is nothing but omega d square. Okay? That is a damped natural frequency squared. So now let me try to write those terms. These are equal to 1 over s minus s plus 2 psi omega n divided by s plus psi omega n square plus omega d square. Okay? Now you see that how this denominator really, maybe I should write, this is omega n. How this denominator is similar to the denominators here in these damped sine and cosine here. The denominators are very similar. And now we're going to try to make the numerators similar as well. Okay? So if instead of s plus 2 psi omega n, if I had s plus psi omega n here, then I would have this exponential times cosine, because it is s plus lambda square plus omega square. Okay? But here, I really do not have s plus psi omega n like this. Instead, I have s plus 2 psi omega n. So here is what I'm going to do. I'm going to write this 2 psi omega n in the following form. So I will write this as s plus psi omega n plus psi omega n. Okay? Then you see that this part is going to give me my cosine e to the minus psi omega nt times cosine omega dt. Okay? What about the other part? The other part is going to be related to the sine here, the damped sine. And that is going to be, so let me write these terms, 1 over s minus, I have s plus psi omega n divided by s plus psi omega n square plus omega d square, and I have minus psi omega n divided by s plus psi omega n square plus omega d square. Okay? Now I have already told you that this part looks similar to a damped cosine, e to the minus lambda t cosine omega t. And here lambda is psi omega n and omega is omega d here. Okay? This is a damped cosine, and this looks like similar to the damped sine here. Okay? But there is a scaling factor here which is different. So here I have omega, which is the same. In the denominator, I have omega square. In the numerator, I should have omega. Okay? So here in the denominator, I have omega d, and therefore in the numerator, I should have omega d. So here what I do is, I multiply and divide by omega d here, this term. Then this part, this part is going to give me my damped sine e to the minus lambda t sine omega t, and the other part is just going to be a scaling constant, psi omega n divided by omega d. Okay? Now let us try to write that function. So I will erase this part. So now let us try to write the time function. Y of t is going to be, this thing is going to be just going to be 1 minus, as I told you, this is the damped cosine, e to the minus lambda t, and lambda is psi omega n, e to the minus psi omega n t times cosine omega t, and omega here is omega d. This is cosine omega dt. Okay? And what about this term? In this case, this term is going to be a damped sine here minus e to the minus psi omega nt sine of omega dt. Okay? And what else? There is also this remaining scaling constant here. Okay? So I would have the scaling constant here. And what is that scaling constant? It is psi omega n divided by omega d. And omega d is omega n times square root 1 minus psi square. This is what omega d is. And omega n's are cancelling, they are non-zero. So I would just have psi over square root 1 minus psi square. So I would have a scaling constant here, psi over 1 minus psi square here. Okay? So this is my time function. So it is just that function we have here. And interestingly, I can further simplify this function a little bit. Here is what I'm going to do. I'm going to write y of t as follows. 1 minus, I'm now trying to, I have already found the answer. This is true for t larger than or equal to 0. I have already found the answer. Now I'm trying to simplify it a little bit. Okay? So in order to be able to make that simplification, what I'm going to do is to combine this cosine and sine term into a single sine or cosine. We will see which one it's going to turn out. So here is what I'm going to do. I'm going to write minus psi omega n t divided by square root 1 minus psi square. I will take this parenthesis. So e to the minus psi omega n t are in both of the terms. And I have 1 over square root 1 minus psi square only in that term. So now let us try to take the parentheses of this quantity. So I would have, this is the same exponential, but here there is no 1 over psi square term. So I add here square root 1 over psi square term, cosine omega dt, and I would have plus, because I take minus parentheses here, both of them would happen to be plus in that case, psi times sine omega dt. And these are in parentheses. So now I would need some help from the pole locations. Okay? I will try to replace this psi and square root 1 minus psi square with some other terms related to the poles here. Here I want to realize the following. Take the square of this thing. It is psi square. Take the square of this thing. It is 1 minus psi square. sum them, you're going to get 1, okay? So square of this term plus square of this term is 1. So they are just like sine and cosine terms. Square of sine plus square of cosine is always 1. So I'm going to try to replace these two terms with sine and cosine of some angles, okay? And this angle that I'm going to consider is this angle, okay? So I'm going to start from the negative real axis, and I will go to this line connecting one of the poles to the origin. Okay, I will call this angle as the angle phi. All right. So this angle is always between 0 and 90 degrees. If it is at 0 degrees, then we have a critically damped system. If it is at 90 degrees, then we have an undamped system. Okay? Because in the undamped case, we have poles here and here. And in the critically damped case, we have double poles at the same location here. So if phi is 0, we have a critically damped system. If phi is 90 degrees, we have an undamped system. Okay? So now what is the sine and cosine of that angle? Well, let me try to write sine phi. Sine phi is this length, divided by the length of the hypotenuse. So this length is omega d divided by omega n. Okay? This length divided by omega n. That is going to give me sine of phi. All right? And omega d divided by omega n is just square root 1. This is omega d divided by omega n is square root 1 minus psi square. And what about cosine of phi? Cosine of phi is this length. It is the distance between the origin and the real parts of the poles. And this length is psi omega n. Okay? This length is psi omega n divided by hypotenuse. Length of the hypotenuse. And in that case, this is psi omega n divided by omega n. This is just going to be psi. So we see that here, this angle, its sine and cosine are just these terms. Square root 1 minus psi square is sine phi, and psi is just cosine phi. Okay? So now let us write this function once more. Y of t is 1 minus e to the minus psi omega n t divided by square root 1 minus psi square. And now instead of square root 1 minus psi square, I write sine phi cosine omega dt plus cosine phi times sine omega dt. Okay? So now this formula might look familiar to you. I hope it looks familiar to you. Okay? So in this case, I have two angles, phi and omega dt here, and sine of the first angle times the cosine of the second angle, cosine of the first angle times the sine of the second angle. They are summed. This is the formula for the sum of two angles, and I take the sine of them. Okay? This is, so if I try to write this here, sine A plus B is sine A cosine B plus cosine A sine B. So we have such a formula. So this is nothing but a single sine function here. And this is the sine of omega dt plus phi, or sine of phi plus omega dt. It's the same thing. Okay? So now let me write this. So I'm going to erase. So remember, I had just summation of a cosine and the sine term, and I was able to write that summation only using a single sine function. And in addition to omega dt, now I had to add some phase to it. Okay, I had to add the angle phi to it. So now if I write that function, y of t is equal to 1 minus, I have this coefficient in the front, e to the minus psi omega nt, divided by square root 1 minus psi square. And instead of this summation, I'm going to write sine omega dt plus phi. Okay? So this is going to be for t larger than or equal to 0. Okay? So this is our final formula here. All right? That we are going to use in our derivations. So now I want you to look at this formula just a little bit. What type of terms do we have? So now in this case, I have this constant. It is what this desired response is. I have the desired response here, and I have another constant, square root 1 minus psi square, 1 over that constant, and I have an exponential here, like this, and I have a sine term given like this. Of course, the sine term is always oscillating. But what about the amplitude of that sine? Amplitude of that sine is determined by this constant term and this decaying exponential. Why is that exponential decaying? Because I have here psi is positive, omega n is positive, so I have a positive number here. They are multiplied by a minus sign times t. Okay? So we see that I have e to the some negative number here, and that is why this exponential is always decaying. So when I look at an exponential, I usually want to determine its time constant. Okay? And if I have e to the minus t over t, something like this, then the time constant of this exponential would be the capital T. So suppose that I want to write this exponential just in this form, and I want to find what capital T is. So I can take this exponential, e to the minus psi omega nt, that is equal to e to the minus t. What am I going to divide this minus t with? In order to, that is going to be my capital T. That is going to be my time constant. And this is going to be 1 over psi omega n. Okay? So the time constant of this exponential is nothing but 1 over psi omega n. So remember, in one of the earlier lectures, I have told you settling time usually happens to be 3 times or 4 times the time constant. Here, at the end of this week, we are going to have 3 times this number is going to be the 5% settling time, and 4 times this number is going to be the 2% settling time. We are going to actually try to estimate these settling times here in terms of the time constant of this exponential, and they're going to be 3 times or 4 times that time constant. And I'm going to explain why we have 3 times or 4 times. Why those magical numbers, 3 and 4. I will try to explain those. The basic reason is this. E to the minus 3 is approximately equal to 0.05, and e to the minus 4 is approximately equal to 0.02. Okay? These magical numbers, the reason for these magical numbers are these. E to the minus 3, if you calculate it using a calculator, it's going to be approximately 0.05, and 5% settling time. So e to the minus 4 is going to be approximately 0.02. So it's going to be determining the 2% settling time. So now I still want to talk a little bit more. What is the frequency of oscillations here? Frequency of oscillations you observe in this underdamped response. We know that it's just going to be the frequency of this sine function. So omega d, which is equal to omega d, which is omega n times 1 minus psi square, is the frequency of oscillations in the underdamped case. Okay? In the underdamped case, which means psi is between 0 and 1. So this is strictly smaller than the natural frequency, undamped natural frequency. What about when psi is equal to 0? When psi is equal to 0, this term becomes 1, so we have omega d is equal to omega n. And in that case, actually, we get the undamped natural frequency, because psi equals to 0 term would be the undamped case. So here, I see that this sign, the frequency of oscillations is omega d. And what about this exponential? And what is omega d? Oh, sorry, I'm jumping really a little bit. I'm a little bit excited. So omega d is the imaginary part of the poles. Okay? So if I wonder about the frequency of oscillations in an underdamped case, then that is just the imaginary part of the poles, which is omega d. Okay? Frequency of oscillations when you have complex poles is determined by the imaginary parts of those poles. What about this decay rate? So this sign is actually decaying with the exponential. Okay? And you see that this decay rate is determined by the time constant of that exponential. Okay? If the time constant is large, then we are going to have a slower decay. If the time constant is small, then we are going to have a faster decay. Okay? How can I say that? If the time constant is large, then psi omega n is small. If psi omega n is small, this exponential is going to decay slower, more slowly. Okay? If psi omega n is small, then this exponential is going to decay more slowly. If psi omega n is large, then exponential is going to decay in a faster way. But psi omega n is just 1 over the time constant of the system. So time constant and the decay rate is going to have the inverse type of relationship. Okay? And what is psi omega n? Psi omega n determines the decay rate. It is related to the time constant of the system. Psi omega n is the real part of the poles. Is determined by the real part of these poles here. Okay? And the distance psi omega n, which is a positive number, is the distance between these poles, the real parts of these poles and the origin. Okay? So if our poles are closer to the imaginary axis, we are going to have a smaller psi omega n, which would mean that this exponential is going to decay more slowly. So as the poles approach to the imaginary axis, we are going to have a slower decay. And is slower decay good for us? No, I want this response to be equal to 1 ideally. Okay? So I want this sine term to disappear quite quickly. So I want a large decay rate. All right? That means I want a large psi omega n for this exponential to decay in a faster way. What does it mean? What does having a large psi omega n mean? It means that we need to have poles far away from the imaginary axis. So far away poles to the imaginary axis means that I'm going to have a faster convergence. In that case, these signs are going to be disappearing much more quickly. Okay? If psi omega n is large, if psi omega n is small, we have poles close to the imaginary axis, and in that case, these signs, these oscillations would be continuing in a much more longer time. All right. So this expression, although I have taken psi between 0 and 1, if I take the limit as psi goes to 0, this expression would still be valid. Okay? So what happens when psi goes to 0? In that case, I have y of t is equal to 1 minus, in this exponential, if this psi goes to 0, e to the minus 0 become 1. So, and 1 minus psi square becomes 1 as well. So I have 1 minus sine here, omega dt, and omega d is given by this formula. If psi goes to 1, this becomes omega n. Omega n. And I have, when psi is equal to 0, in that case I would have just this sine omega nt plus phi. Okay, so you see that in the case, and if you look at this case, when psi goes to 0, real part becomes 0 and the imaginary part becomes omega n. So phi is just 90 degrees in that case. So I have just this 1 minus sine omega nt plus 90 degrees. Okay, so I would just have this term. So this is actually the undamped response, okay? By just deriving the underdamped response here, we have derived the undamped response as well. And sine omega nt just becomes, it is just cosine omega nt, okay? It just becomes this, 1 minus cosine omega nt. So this is the undamped response case, and you see that it is 1 minus a cosine which is neither growing nor decaying. So in that case I would have a sine, and it would have, and the sine amplitude, cosine amplitude is 1. So this response would start here and it would go to 2, and then it would come back and it would hit 0 again, and it would go to 2, and that is what undamped response is. So this was just a derivation of the response of an underdamped system, and the next task of the coming lecture is going to be to determine this TR. What would be TR in terms of this psi and omega n or omega d? And how can I find TR in that case? TR is the first time instant that we reach the desired, that the response hits the desired value. And if I want to find TR, then I need to solve the equation y of t is equal to 1. What is t? And in that case, this term has to be equal to 0. And by solving this term, the equation coming from this term being equal to 0, we're going to find what rise time is. What about peak time? Peak time is going to be given at this time instant, and at this time instant, the response has a peak. How can I find the peak time by using such a formula? The answer is going to be related to the derivative, okay? So this time is, at this time instant, the derivative of that function has to be equal to 0. That is going to give us what TP is. And how can I find the maximum overshoot? It is going to be, I will find that peak time, I will evaluate that response at that peak time, and I will subtract 1 to find what MP is. That is going to give me the maximum overshoot. And finally we will come to the issue of settling time. And for finding the settling time, I will draw some envelopes of this response, some upper bound and some lower bound. And then we are going to find the settling time based on those upper bound and lower bound. And probably the most approximate result is going to be the settling time. We will see that all of the other quantities, TR, TP, MP, we will be able to find exactly. But the settling time, we're going to use an approximate result, a very, very approximate result. It is because it is really very difficult to find such an intersection of this curve with these region boundaries. Okay, it's very difficult to find these intersections, and there might be many of those intersections, and we have to try to find their maximum. If we want to find the settling time exactly, then we have to find the intersections of these region boundaries with the response, and then we have to take their maximum. Okay, but really this is not possible. That is why we're going to come up with some approximate formula which are going to be the 3 times the time constant and the 4 times the time constant at the end. Okay? But that's going to be all for this first lecture. Thank you very much for watching.